So we're almost done our videos in chapter 13 and for the semester, and we're going to talk about electron pair geometry in this video and molecular geometry if we have time. So before we do that, we need to talk about something called valence shell electron pair repulsion theory, or VESPER theory. And the idea is pretty simple, is that the electron pairs that we've been using in Lewis structures repel each other. So they distribute themselves in positions around a central atom that are as far away from each other as possible to minimize the potential energy of the molecule. So we have three different types of geometries here that we can see, or I should say arrangements. If we had a central atom and we have these two atoms here on the outside, right? It might be more of a straight or a linear geometry where there's 180 degrees between the two atoms bonded. If there's three atoms here, well, now we're going to have a little bit of a different angle, right? They're going to move again to get as far away from each other as possible. In this case, it's 120 degrees. And if we had four, they're going to arrange themselves in such a way here. Well, now the angle is 109.5 degrees. We'll talk a little bit more about that as we go through this video, but that's the idea basically, as far as an introduction to VESPER theory, is that these bonding pairs are arranging themselves or getting far away from each other as possible to minimize that repulsion. Okay, so you could picture this with balloons. So we have, again, 2, 3, or 4. Okay, so we're going to call those electron domains right now. So if you have two electron domains, let's say you have a central atom here, and these balloons represent domains, okay? If you have two domains, okay, the electron pair geometry is linear. That was that 180-degree angle. And we're talking about domains as, you could think of each bonding pair here as a domain. So that could be a domain there, and that could be a domain there. Or I should say, really, not only bonding pairs, but every pair of electrons as a domain. That's the best way to think about it. And so these are things just kind of to memorize. The bonding angle between this is going to be 180 degrees. Okay. So if you move over here for when we have three electron domains, right? We have the central atom in the middle, and then it's kind of like so. Okay. This electron pair geometry is called trigonal planar, okay? And the bond angles here are going to be 120 degrees. And again, this is just something to memorize, and we're going to do lots of examples together. And then finally here, if we have four domains here, so 1, 2, 3, 4, okay? The bond angle between here is going to be 109.5 degrees. And this is something called tetrahedral. Again, when you have the four domains here, which could be bonding pairs of electrons or non-bonding lone pair electrons, which we'll see as we do some examples of this, okay? So that's kind of the idea with electron pair geometry. You have linear, trigonal planar, or tetrahedral. Okay, so let's move over to molecular geometry now. So molecular geometry just follows naturally from electron pair geometry. Okay, so if atoms form bonds with two atoms, the angle between the bonds is the bond angle. Okay, so you could see here a water molecule, right, where you have an oxygen, right, and the hydrogens right here. So one hydrogen, one hydrogen. If you look at a water molecule structure, the bond angle, right, is given here. It's the angle between the bonds, right? Carbon dioxide molecule, you have carbon here, and oxygen here. It is a linear molecule, so there's 180 degrees between the bond, right? It's linear, okay? So, and this comes from, or is related to electron pair geometry, which we'll see in a second. So I'm gonna just, on these slides, just list molecular geometries that for you to, somebody keeps blowing up my phone over there, so I'm sorry if I keep looking, but I'm just going to list some. There's a table, I think, in your notes and in your textbook that you can have for reference. I there's maybe not a really good way to memorize these other than to do some example problems and have the list in front of you when doing those problems on an exam or a quiz. So here's all the different flavors of molecular geometries. Again, they are the angles that the bonds are at, okay, and they have to do with the bonding pairs here. So let's say you had an electron domain geometry of 2, which is something we saw before. Okay, so the electron pair geometry is linear. Okay, if both of those electron domains are bonded, right, to atoms, okay, the molecular geometry is also going to be linear. And I understand if this kind of doesn't make any sense right now, we're going to do problems and it's going to make sense. I hope, but I just want to go through all of this and then you have these to refer back to when we do the example problems, okay? Because like I said, right now it might be a little bit confusing. So again, if we have 3 electron domains, like the balloon example, our electron domain geometry is trigonoplanar. If each one of those domains is a bond, right, to an atom, then the molecular geometry is also trigonoplanar, okay? And I'm showing here some examples of molecules forming that planar geometry where it's flat, right? The molecule is flat, fairly flat. Okay, so now here's where it starts to change a little bit. Let's say you have electron domain of 3, so your electron domain geometry is trigonoplanar, but let's say you only have 2 regions that are bonded, okay? So the molecule is going to look something like this. So you have an electron domain out here that's not bonded. Okay? So the molecule, the resulting molecule, is going to look like this. So it's going to be considered to have an angular geometry, okay? So when you have electron domain geometry of 3, but only 2 regions are bonded, it has an angular geometry. So moving right along, again, if you have your electron domains of 4, oh, I just copied this twice, it looks like. Yep, so that's a typo. So number of electron domains is 4. So electron domain geometry is considered tetrahedral, something we saw before. If all 4 of those regions are bonded, then the molecular geometry is also tetrahedral. However, if only 3 of those regions is bonded, okay, and this one here, let's say on the top, is non-bonded, okay, then it's going to have this trigonal pyramidal is what it's called geometry, where you can think about it, it looks kind of like a little pyramid maybe, where these guys are all kind of meeting up on the top, like a little tripod, okay? That's how the molecule is going to look. And then finally, if we have 4 domains, electron domains is tetrahedral. If 2 of those regions are bonded, like here, and we have a region here and a region, excuse me, let me erase this real quick. If we have a region here and a region here that are non-bonding, okay, the molecule is going to form a bent molecular geometry, okay? So I hope at least that you're seeing that your electron domain geometry doesn't really change so much. It's, you know, if it's tetragonal, it's going to be tetragonal no matter how many regions are bonded, right? The shape, I mean, of the electron domain geometry doesn't change. If you have 4 electron domains, it's always tetrahedral, but your molecular geometry can change, is what I'm trying to say here. So how do we predict these geometries? How do we find it? Like I said, that was just a bunch of maybe things that I was saying, but how do we kind of take that knowledge and apply it to problems? Well, first step, we got to draw the Lewis structure. So if you're not familiar with that, go back to the other video, learn how to draw Lewis structures, because I'm going to go much faster drawing them in this video. Count the electron pairs around the central atom, both bonding and unshared, okay? And then from that information, we're going to be able to determine the electron pair and molecular geometries. And it says here to do it by reason rather than memorization, but to be honest with you, I would just have the charts in front of you or the slides here, print them out, write down in your notes. And so when you do the problems, you can just refer right to it and you'll have a much easier time. Okay, So let's just do some practice problems here. It wants us to state the electron pair and molecular geometries of the following molecules. Okay, so for sake of space, I'm not really going to spend a lot of time going over counting the valence electrons and going over all the rules for drawing Lewis structures. So I'm just going to draw the Lewis structures basically. And then you could try to do them on your own. So here you go. Here's number 1. Okay. So what is its electron pair geometry and molecular geometry? Okay. Well, remember what we're going to do here. We're going to determine, right, count all the electron pairs around the central atom, bonding and non-bonding. So there's 1, 2, 3, 4, or excuse me. Sorry. 1, 2, 3, 4 pairs of electrons. I was counting singular electrons there. So pairs of electrons. I got so used to the Lewis structures that I'm just counting. Okay. So there's 4 pairs of electrons here. So another way to say that is 4 domains. Okay. So for 4 domains, right, the electron pair geometry tetrahedral. I think I spelled that right. But the molecular geometry, right, if all 4 of those are bonding pairs, right, then the molecular geometry would be the same as the electron geometry. We just go back one, right? If they were all bonding. But that's not the case. We have 4 domains, but only 3 regions are bonded here. So that means our shape, right, is going to be trigonal pyramidal. So I'll just say trig. Okay, and hopefully that made sense. So that's all you're going to do for these problems. All right, so let's do some more. B. So this is carbon tetrachloride. If you remember for your the naming chapter. Okay, and I'm only concerned about the central atom. So about that carbon, all right, there's 1, 2, 3, 4 domains again, right? So electron pair geometry is tetrahedral. And because all of those are bonding regions, the molecular geometry is also going to be tetrahedral. Okay, so that's how we're going to do these problems. So I'm just going to clear all of the ink in the slide, and let's just keep going. Okay, so here's our next compound here. This is kind of a weird one. Boron actually is an exception. I don't know if we came across boron before, but boron can have less than an octet. Okay, boron can have less than an octet. That's maybe a mistake if I didn't put that in the last video. So he's perfectly happy being this way with 6 valence electrons. Okay. And you may have noticed that when you ran out of valence electrons putting this together. Okay, so let's see here. He has 1, 2, 3 bonding pairs. Okay, so 3 domains. And all 3 of those are bonding pairs, as I mentioned. Okay, so electron pair geometry, molecular geometry. This is going to be trigonal. Oh, planar, right? And this is also going to be trig planar. All right, and I'm just referring back to those slides before. Okay, so this is right here. 3 domains, all regions are bonded. So it's trigonal planar. Okay. Next, right here. So this guy looks something like this. Okay. So again, we're only worried about the central atom, which is the oxygen. So 1, 2, 3, 4 pairs. Okay, so 4 domains. So electron pair geometry is tetrahedral. Molecular geometry is actually going to be bent because 2 of those regions are bonded. Okay, and if you just go back, 4 regions, 2 are bonded, it's bent for its molecular geometry. And that's kind of how I drew it. Its shape. Okay, so clear all the ink. Let's do one more. So this guy, or actually, why don't you try to do this guy? Okay, so write down the Lewis structure and then go ahead and write down its shape. Okay, so here's its Lewis structure. Okay, we're only worried about the nitrogen here for our geometry. So there's 1, 2, 3, 4. 4 domains. Okay, so electron pair geometry is tetrahedral, and molecular geometry is trigonal pyramidal. Did I spell that right? Let's see here. Yep. Let's see here. Pyramidal. I think so. If it's wrong, forgive me. But there you go. Okay, so that's how you do these problems. So now in the next video, we're going to look at how to do the geometry of multiple bonds.